This project is on cryptology and quantum computers. The goal of this project is to, 1, gain insight into how cryptology works and how it is applied into our everyday lives. 2, explore quantum computers and their computing power. And 3, answer the question as to whether these powerful quantum computers have the ability to destroy our modern cryptographic security methods. Naturally, the question that arises is, what is cryptology? Cryptology is the study and practice of techniques for secure communication while in the presence of third parties, which are known as adversaries. Some of the areas where we need and use secured communication are in 1, e-commerce, or otherwise known as online shopping. 2, in chip-based debit and credit cards. 3, digital currencies, for example, Bitcoin, which currently right now is valued at $18,000 a share. And 4, emails. Now, in order for communication to be secure, we need to develop a system that does the securing, and this type of system is known as a crypto system. There are different types of systems that are used these days, but the one that we will look at today is what is known as public key. A public key system is a system where a person will create what is known as a private key, or code if you will, and a public key. Now, the person who creates the public and private key will share the public key with everyone so that they are able to encrypt and code messages to send to them, which they are only able to decrypt. So let's take a look at an example. Suppose Bob wants to send a message that is private and secure to Alice. Now, in a perfect world, Bob could do that without worrying whether anybody would try to read his message or tamper with it. However, the world is not perfect, and one of Bob's adversaries named Eve is waiting to cause some trouble. Bob remembers that he received at one time a purple public key from Alice and was told that he could use the purple public key and an encryption program to code his message into what is known as a ciphertext. He then could send the ciphertext to Alice via the internet, and once Alice received this ciphertext, she could decode the message because she was the one who created the public key, and she is the only one that possesses the pink private key that is able to decrypt the ciphertext back into its original message. So let's take a closer look at how Alice generated the private and public keys allowed for this secured communication to take place. What Alice did is she first chose 2 distinct large prime numbers and then multiplied them together to get a value. Let's call this value n. Next, what she did is she used the function known as the Carmichael's Twin function to create another value. Next, what she did is she chose an integer, we'll call it e, and chose that integer to be less than her function value, but greater than 1. This allowed her to develop the public key. So the public key consists of the value of n and the integer e. Finally, what she did is she created the private key. She did this by multiplying her function value by 2, adding 1, and then dividing by her integer value e. Essentially, what happens is Bob would take his message and create a numerical value for it, say m. He would then use his public key to raise the value of m by the integer value e, and then divide by N. Now the remainder of this value is what is known as the ciphertext. Naturally, in order to decrypt this message, Alice, who possessed the private key, denoted as D, could undo the operations that Bob performed on the message, and then in doing so, retrieve the original message. Now, the idea behind this really large number is that it takes a long time to go through all the different possibilities of what the private key could be. In fact, if you had a 128-bit cipher, the number of possible keys with 128 bits is 2 raised to the power of 128, which is 3.4 times 10 to the 38th possible keys. Now, this type of breakdown would take anywhere from 10.79 quintillion years to figure out, to go through all the different possibilities. Thus enters in quantum computers. Now, the difference between a classical computer and a quantum computer is that classical computers code data in binary units known as bits and are represented as either a definite state of a 0 or 1. Quantum computers, on the other hand, take advantage of the superposition states of particles and use qubits, which allow a bit to be simultaneously in both the 0 and 1 state. Now, to illustrate this idea, suppose we have 3 classical bits. Then what this implies is that we have 2 to the 3 possible outcomes. Therefore, the 8 possible outcomes are 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. However, out of these 8 possibilities, the classical system is limited to being only one of the 8 possibilities at a time. This would require 8 separate mathematical operations. On the other hand, 3 qubits can represent all 8 outcomes simultaneously and requires only one mathematical operation. Basically, if you had, say, n qubits, it is equivalent to computing 2 to the n classical bits. So a quantum computer is working in parallel states and theoretically improving our computational speeds. So does that mean that quantum computers will destroy our cryptographic systems because of their increased computational power? Well, don't panic. Quantum computers are still in the infant stage of development. Bob does not need to worry that Eve will decrypt his message that he's sending to Alice. However, people are working on developing different types of methods in preparation of quantum computers that will someday soon be here. Some of these different new techniques are quantum cryptology, lattice-based cryptology, code-based cryptology, and multivariate cryptology. So while quantum computers are on the rise, people are taking the necessary steps to make sure that you can still shop online, send money, buy Bitcoin, and enjoy life.